It's time for fun with math, and today we're going to talk about something called exponential functions. But first, let's look at today's question. And so today's question is, which table is exponential? And so you kind of look at these tables, and you can see the pattern that's taking place. And so here, if you look, the inputs are increasing by 1. And so the outputs here, they look like they're changing by what? And you can basically see the pattern. It goes 0, 3, 6, 9. I would guess the next one here will be 12. Because each time it looks like you're adding what? You're just adding 3. All right, so just adding 3 each time. So that's the pattern for that table. Whereas over here in table B, if we look at it, the inputs are also increasing by 1. But the outputs are doing something different. So here it goes 4, 8, 16, and 32. So they're not increasing by a constant number, because if they were, this would be plus 4, and then plus 4 would be 12, but it's not, it's 16. But you can guess at the next answer. So 4, 8, 16, 32. I bet the next one on the left, of course, would be 3. On the right, I bet it would be 64. Because what you're doing here is you're not adding, but you're doing an operation that's similar to addition in a way. It's like repeated addition. It's multiplication. So here, we're basically multiplying by 3. And let's use, I guess we can use the, so we're multiplying by, not 3, I'm sorry. We're multiplying by 2 each time. So times 2, times 2, times 2, and times 2. And so which one of these tables is exponential? Well, remember table A, this was the idea of a linear function. So this is linear. So that means table B must be this idea of exponential. So the idea of exponential is you basically multiply by the same number each time. And that's really why it's important. So if you're looking at something, some data, and it looks like you're increasing not at a constant rate of change, but a constant, what we may say, percent rate of change, where you're multiplying by the same number each time, then it's exponential data. You can even come up with formulas for this. So remember this one here, the idea is at 0 you start at 6, so the formula would look like this, y equals 6, and you're adding 3 each time, so it'd be plus 3x. And normally we like to write that in mx plus b form, so we normally write y equals 3x plus b. But the formula is easy to figure out, so in this case, plus 6. Over here, the formula is just as easy to figure out. At 0, you're starting at 8. So your y, what it'll be equal to is you'll start at 8. But instead of adding the same number each time, you're going to multiply by the same number each time. So then we're going to multiply by, so times 2. And in this case, right, so it's not 2x, but it's 2 to the x. Because you're multiplying by 2 each time. So if x is 1, this will be times 2. If x is 2, this will be 2 squared, just 2 times 2. So you get 4 times 8, which is 32. And if x is 3, this will be 2 cubed, which is 2 times 2 times 2. Right? So if it's 2 cubed, that means do 2 times 2 times 2. And so this is the idea of an exponential function. So basically, what is an exponential function? The idea is you have this sort of constant percent rate of change. And so before we think too much about that, let's just look at an example involving a table, so you can see a problem that's a little bit harder to see exactly, but once we do it, it'll make sense. So here we want to work with some exponential tables. So it says use the table to answer the problems below. So let's talk about these things. I haven't really defined them yet, but they're sort of intuitive, and that's what we want to do. We want to develop some intuition working with exponential functions, basically. So determine what's called the initial value and then the growth factor. All right, so let's look at this. Over here, if I asked you, what is the initial value, what would you choose? And so hopefully you're like, well, there are a couple choices. Sometimes people look at 1 and say, hey, 1's the first one, right? So the initial value might be 7.2. That's not how it works. It actually starts at 0. And so the initial value is just the number 6. So here, their initial value would be the number 6. Whereas the growth factor, right? The growth factor is by what you're growing by. And if you think about this, this makes actually a lot of sense. It's growth because the outputs are getting bigger. If the outputs were getting smaller, we actually would call it decay. And we'll talk about this in a minute. And we want to know how they're getting bigger, and it's a factor. And so when you think of a factor, hopefully think of multiplication, right? So when I think of a factor, I think of like a microscope that has like times 500, like it increases your eyesight by 500, by a factor of 500, or by a factor of a 1,000 or something like that. So really what this is saying is, what number are you multiplying by to get from here to there, or from here to there, or from here to there? Right? And so to figure this out, I want you to think about the problem we just did before. So, how can we figure out what number we added by here? Well, you just subtract, right? 3 minus 0 is 3, 6 minus 3 is 3, 9 minus 6 is 3. That's what we did. Over here, though, it's different. So since you're adding, we subtract to figure it out. Over here, we're multiplying. So we don't subtract, we actually divide. So if you take 8 divided by 4, you'll see it's 2. 16 divided by 8, it's 2. 32 divided by 16, it's 2, and so on. So we can apply that down here, and this is what leads to this sort of constant percentage rate of change idea. But if you take 6 divided by 5, you'll see that's equal to 1.2. And then if you do 7.2 divided by 6, it's always the final divided by the initial. You'll see that's 1.2. And if you do 8.64 divided by 7.2, and of course you'll need a calculator to do these, you'll see that's also equal to 1.2. And so our growth factor in this case, what number are you multiplying by each time to get to the next number, is 1.2. And so now, if you want, we could actually write down the formula for the exponential function. And it's really not that hard if you think about sort of the pattern, sort of the form, to find the formula. So the idea is we have y equals, and you start with your initial value, so you start at 6, and then each time you're multiplying by the number 1.2, and then each time in this case you don't multiply by x, you raise it to the x. And you can check to see that this formula works. Like you could plug in 1, and then if you plugged in 1, you'd have 6 times 1.2, and you can check that on your calculator and see, yes, that is 7.2, so 6 times 1.2. Right, you could do even 2 to make sure that it's correct by plugging in 2, and that would be 6 times 1.2 squared. And you can check that on your calculator, and you'll see that that's actually 1.2 squared. And let's write it like this, so 1.2 squared, and you'll see that that's actually 8.64. All right, so we hopefully we understand kind of now what the initial value is. That's where it starts. What a growth factor is. That's the number you're multiplying by each time. How you can put that information together to write down the formula, and we'll talk about more of this in a minute. But this one's always an important question. By what percentage is it actually growing? So you're going from 5 to 6, 6 to 7.2, and 7.2 to 8.64. What is that percent rate of change in a way? But what's the percentage it's growing by? And it's actually pretty easy to see. So the growth factor here is a 1.2. If you think about this, the 1 is sort of the whole part that we started with, and the 0.2 is the additional percent. For example, just think about this. Suppose you were making $50,000 a year, and your salary grew by 5%. What would your new salary be? Well, one way to calculate that pretty fast is multiply this by 1.05. If you multiply this by 1.05, what it's going to give you is the whole piece. That's the 1. It'll be the 50,000. Plus this extra little 5% right here. 0.05 is really 5%. Written as a decimal. And so then 5% of 50,000 is 5,000. Not $5,000, sorry, it's $2,500. Right? 5,000 is 10%, and so 5% would be 2,500. So total, you would get your new salary would be $52,500 basically, right? You can do the same thing, so that's growth, but you could actually do the same thing as decay. So suppose you were making $50,000 and for some reason you got a 5% cut in your pay. So to figure out what your new salary would be, you'd multiply this not by 1.05 but by 0.95. The idea being, if you raise by 5%, you get 105% basically of your old salary. Whereas if you decrease by 5%, you only get 95% of your old salary. So if you do this, basically what's going to happen, if you multiply this by 0.95 on your calculator, you'll see that you have $47,500 for your new salary. So you lost $2,500. But you can look at these numbers here, and it's really important that you can understand this, because you apply this to your salary all the time, because when you do get raises, it's sort of like a sort of percentage raise, like you get a 3% raise or a 5% raise or something like that. So here it's real easy to see that you got a 5% raise, where here you lost 5% of your salary. So here would be growth by 5%, and there would be decay by 5%. So when I look at this and you're taking 6 times 1.2 to the x, my brain immediately says to me, oh, that's a 20%. 0.2 is a 20% growth. So that's huge, which is always really exciting to me, because I think 20%, man, if my salary went up by 20%, I'd be very, very excited. All right, so let's talk a little bit more about how this works. In particular, we want to talk first about graphs, and then we'll get into the formulas. So for exponential functions, there's basically two graphs. And so let's take a look at the two graphs, just sort of like with lines, there are two graphs. They either increase or they decrease. Well, for exponential functions, they're either going to grow or decay. So an exponential function, basically the formula kind of looks like this. And as a result, the graphs look something like this. They kind of come up and go up like this. And they have a horizontal asymptote. They have a horizontal asymptote here at y equals 0. All right, so there's a horizontal asymptote at y equals 0. And this is what we mean by growth. And of course, there's also then decay. And decay looks kind of similar, it just goes the other way. And so we can give an example of decay over here. Instead of going up, it's going to go down basically. So it's going to kind of come up and then go down like this. And it also has a horizontal asymptote at y equals 0. So I'll draw this little horizontal asymptote here at y equals 0. And then we can actually label this sort of pieces here. So we have this formula, f of x equals c times a to the x. C is called the initial value. So the initial value is what happens when you start at 0. It's basically the y-intercept. So that's the height c, and that's height c. And then this a right here, this a is called the growth or decay factor, depending on whether you're growing or decaying. And you can actually use that to figure out whether it's growing or decaying. Sort of like we can use slope. If you have slope, y equals mx plus b, if you draw the equation of the line and it looks like this, I know m has to be bigger than 0. Whereas if it goes down, I know m is actually less than 0. A similar idea can be applied to exponential growth, and this has to do with the value of a. So if a is, and think about this, if a is bigger than 1, you're going to get growth. And it's really kind of obvious. If you multiply by a number bigger than 1, something's going to get bigger. So if you have like $50,000, let's say, and you multiply by 1.5, it's not going to get smaller, it's going to get bigger. And so that's why you get growth. Whereas if a is less than 1, and a will always have to be positive, so basically it's less than 1, it's between 0 and 1, you're always going to get decay. And you can think about that too. It's like if a is a half, if you have $50,000 and you multiply by half, it doesn't get bigger, it gets smaller. All right, so it's not that I have to necessarily memorize these things. They make sense, and so I try to make sense of them. That way I don't have to memorize them, because there's already a lot of things that I need to memorize. There's also a formula for what's called the growth or decay rate, sort of what we did before. And so that's a equals 1 plus r. So for example, before we had a equal to 1.2. If you like formulas, you could say, well, 1.2 is equal to 1 plus r, and solve for r, and you find r is equal to 0.2. So let's write a 0. So 0, let's write 0.2. So when you subtract 1 from both sides, r is 0.2. So the percentage rate of change is 20%. So you can use that formula if you like. I don't really use this formula that much because, again, I don't like to memorize formulas if I don't have to. I much prefer to memorize ideas and how I use them because there's just so much to memorize all the time. Okay, so I think that's good. We talked about the graphs. There's two types of graphs, growth and decay. You see the formula here, f of x equals c times a to the x. You won't have to memorize this formula, of course. I will give it to you on the exam, but you'll have to know c is the initial value and a is the growth or decay factor. But let's look at a problem. So here's a problem. We want to use the graph to determine the formula for the exponential function y equals c times a to the x. So this is similar to what we've been doing before. So remember before I've been giving you stuff like here's the graph of a line, or here's the graph of a parabola with some sort of vertex right here, and you're supposed to find the formula, right? Y equals mx plus b for the line, y is equal to a times x minus h quantity squared plus k for the parabola or quadratic function. So now we want to do it for exponential functions, and it's really not that hard. It's sort of a plug and chug exercise, and a lot of times you can use your intuition, especially in this case. So if you have this formula, y equals c times a to the x, if you use your intuition, my intuition would say, okay, well, these c and a, they actually have meaning. So c is the initial value. So if you look at this, it's actually pretty easy. C is just this height, the number 2. So I can use my intuition, but I could also just use a coordinate pair, right? So this is just telling me if you plug in 0, you get out 2. So when you plug in 0, so c times a to the 0, it says you get out 2. And of course, a to the 0 is just 1. Anything to the 0 power is always 1, so you just get 2 equal to c. So there's one piece of information there, which tells me now that y is equal to 2 times a to the x. And I use this piece of information to find c, and so up here I can use this piece of information to find a. So this says if you plug in 1, you get out 10. So the out goes in for the y, because that's the output, so 10 is equal to 2 times a, and the input is the x, so a to the 1. Of course, a to the 1 is just a, so it's really just 10 equals 2 times a. You divide both sides by 2. That tells you 5 is the same thing as a. So now that I know what a is and I know what c is, I can write down my formula for the function y equals 2 times 5 to the x. And so there's the formula for that exponential function. And you can use y, or you could use f of x. It's really up to you which notation you want to use. You should be familiar with both of them. You can. All right, so let's look at another example. It's a little bit harder, right? This one wasn't so bad because it actually gave you the initial value. Let's look at an example now where they don't give you the initial value. So here we want to find the formula and graph the exponential function with f of 1 equal to 24 and f of 3 equal to 6. So first, let's just plot those points so we can kind of see what the function is going to look like, because you can decide real quickly whether this is going to be growth or decay. So it says if you plug in 1, you get out 24. So we're not going to draw this to scale, but we're just going to get them in the right spot. So there's 1, 24, input 1, output 24. And this one says f of 3 is equal to 6. So over here at 3, let's put it right here, we get out 6, so 3 comma 6. So it looks like, if I had to guess, I'd guess it kind of comes up here, goes down here, and I'm missing that point, but that's okay. And it comes down here and then sort of levels off like that. So I'm guessing right here, let's make that a little bigger, that it's not actually growth, this is actually decay, which is nice because now I know that my a, which is not going to be a growth factor, is a decay factor, it's going to be between 0 and 1. But that's not really, you don't really have to know that to solve this problem. What you do need to know, though, is the formula. So let's remind you of the formula. Since they're using function notation, we'll use function notation. So f of x is equal to c times a to the x. And now in this problem, we can't immediately say what c actually is because we don't know the initial value. I mean, I can tell you that it's bigger than 24, but I don't know how much bigger than 24 it actually is. So we'll have to use the information they gave us, in particular this 1 comma 24. So it says if you plug in 1, you get out 24. So over here, this is the output, so 24 is equal to c times a to the 1. which is really 24 equals C times A. And so that's one piece of information. There's not much I can do with this at this moment, but I have another piece of information right here, which says if I plug in 3, I get out 6. So I can do the same thing here. The output is 6, so 6 equals, and then C times A to the 3. And so what I have now is basically I have two equations. Here's 1 and here's 2, and I have two unknowns, C and A. C and A. So what I can do is I can use these two equations and use one to solve for A or C and plug into the other, and then I can solve for that unknown constant, basically. So let's look. Which one would you like to solve for here, C or A? It really doesn't matter. I think I'll just solve it for C. So what I'm going to do is I'm going to take this and I'm going to divide out by A on both sides. So I'll divide out by A here and divide out by A. And so basically, what do I have? I get 24 divided by A is equal to C. And now I can take this and I can plug it in right here for C. So this is going to be 6 equals, and this will be 24 divided by A times A cubed. And so you have an A on top and an A on bottom, so they're going to cancel. So I'm going to get 6 equals 24 A squared. I'm trying to solve this for A now, so I'll divide out by the 24 on both sides. And so now I have 6 over 24 on the left, which is really 1 over 4. Remember, 24 is 6 times 4, so the 6's just cancel. And I have A squared left over on the right. And then undo the square, I do the square root of both sides. Now, you do plus or minus, but remember, A is always positive. Right? We didn't talk about exactly why that's the case. Maybe we should. I should have mentioned that before. But the reason why A is always positive, like if A was negative, like A is negative 1 and to the x is any real number. So if x was like 1/2, that would be negative 1 to the 1/2. And remember, what does it mean to have a fractional exponent, especially 1/2? That's actually a square root of negative 1, which is a complex, or if you want, imaginary number. And we want to stay away from those. So, but it's a complex number. So we always force our a's to be bigger than 0. So 0 is always less than a. Right, a is always bigger than 0 if you want. All right, so you take the square root of both sides. It is plus or minus, but you don't have to worry about the minus part. So we just get 1/2 is equal to our a. And if 1/2 is equal to our a, we immediately know that c is equal to, it says 24 over a. So it's 24 divided by a, so divided by 1/2. We multiply it by the reciprocal, so 24 times 2 over 1, which is actually equal to 48. And so we know a is 1/2, c is 48, and so we get our answer, f of x is going to be equal to 48 times 1/2 to the x. So in this case, I like to use parentheses. It looks a little bit nicer. But that's our answer. That's our formula. Remember, you can check this with your calculator, which is kind of nice. So here's my calculator. And if you want to check it, it checks relatively easily. You can just hit on and hit y equals, and you can graph this thing. So you can do 48 times, or you don't even do times. You can do 48 and just do left parenthesis if you want. 1 divided by 2. In parenthesis, and we can do raised to, and then put an x. We can make a window. We just have a standard window here. That's great, negative 10 to 10. So let's just do a standard window so you can kind of see it. Oh, but we're not going to see much of it, right? See, we're not going to see much of it because it's 124, right? But you can trace it. You can actually trace this and see if you plug in 1, what do you get out? So 1, enter, you get out 24. 3, enter, you get out 6. And so you can, basically say, like, that's definitely the exponential function that fits that data. All right, so that's basically a check because I checked it with my graphing calculator. All right, so let's move on. And so the last thing we always want to talk about when we learn about a function like exponential function here, we want to talk about problems with modeling. So, how are these functions used to sort of model things? And it becomes real apparent how useful they are and how common they actually are once we look at these word problems. So we want to find an exponential formula that models the given situation. So we have two different situations. So in the first one it says in 1970 a certain city had a population of 22,000. Since then the population has grown at a steady rate of 3.2% per year. So if we want to find a formula that's going to model the population basically in the future, and this idea is relatively important if you think about it. If a population continues to grow, you have to increase sort of the amenities for that public, like sort of like schools, fire stations, police, all kinds of things have to be planned basically. And so let's see if we can't find the formula for this. And so we just start with the form of the formula, and it doesn't matter. You can use this old f of x equals c times a to the x if that's what you feel most comfortable with. I typically kind of change this up a little bit. Since I'm modeling population, I might call it p and I might call it of t. So I like to practice this to get comfortable using variables that make sense. P stands for population, t stands for time, and I probably write this as it'd be p naught, because p naught is the initial population, and we do this a lot in physics and chemistry. We use this little symbol naught to mean the initial whatever, and then I would use times a to the t. All right, so I like to mix it up a little bit and try to make my variables here sort of in constants reflect the problem that I'm working with. And then it's a little easier for me because the idea is you just got to figure out what P naught is. What's your initial population here? And that number is given to us. It's just 22,000. So my P naught is equal to 22,000. And then the only thing that's a little bit difficult sometimes for us to figure out is what is our growth factor. Now I know it's a growth factor because it says it's growing. And I know the percentage it's growing about. It's 3.2%. Now remember, we'll have to write that as a decimal, and it's not too hard to figure out how to write it as a decimal. You can divide by 100 or just move the decimal to the left 2 places. So as a decimal, that's 0.032. And so my A is actually equal to, and sometimes you guys think, no, A is just 0.032. So if you wrote this, I'd say that's a great idea, but it's wrong because that's not growth. If you multiply by 0.032, you're not going to grow. You're actually going to decay. So what's wrong here is it doesn't have the whole piece, right? So you need that whole piece, which is that 1. So it's actually 1.032. And the 1 comes from the whole. If you multiply it by 1.032, what you're telling me is you're going to give me the whole piece, the 22,000 people back, plus that extra 3.2%. So my formula for this one, P of t, is equal to 22,000 times 1.032 to the t. And again, the idea is you have this whole piece and you're basically just adding the percentage because you're growing 0.032. Now we can compare that to the next problem where you're not going to grow, you're probably going to decay. So here it says a company's total assets were valued at 1.2 million in 2010, but they have decreased at a constant rate of 2.5% per year. So clearly this is going to be decay, one, because we're trying to compare and kind of contrast these two types of problems, but it says decreased at a constant rate. So in this case, instead of using population, since I'm modeling assets, I'll use A. I'll say A of t is equal to, I like to be, practice this, so A naught, and then I'll still use A to the t because A is my growth or decay factor, although in this case it's going to be a decay factor. And so what's A naught? A naught's my initial assets, which looks like to be $1.2 million. So I'm going to use 1.2, which implies that all the outputs are going to be in terms of millions of dollars. So, when I say 1.2, I really mean 1.2 millions of dollars. And then my A is a little hard to figure out. But if you think about it, it's not that bad. Here we added 3.2%. Here we're going to subtract. So our A, instead of A1 plus, it's going to be 1 minus. And of course, as a decimal, this is 0.025. So it's going to be 1 minus 0.025, which you could figure out on a calculator if you think about it, just 0.975. So that's the decay factor. That's the number you're going to multiply by. And it says you basically lost 2.5%. So my A of t will equal 1.2 times 0.975 to the t. And remember, you can check your answers by just plugging in numbers. I mean, you know that this is going to decrease by 2.5%, so you can figure out the assets in basically 2011 by taking 1.2 and multiplying by 0.975, and you'll see you get the same answer as if you plugged in 1 down here. So you can check these if you like to. Right? So those are two sort of basic problems trying to find formulas. Let's do the next problem, which is you're going to find a formula, but then you have to use it to actually do something, right? So up here, we didn't really ask you anything, how do you use these formulas to do something? Like, what would the population be in 1975? So you could actually ask that question. Or how long will it take for the population to reach 45,000? Right, so these are input and output questions. Let's do an example that has one of those. So here we have the value of your car is decreasing 12% a year. So it's decreasing by 12% per year, and the car is currently worth $9,749. We want to find a formula for the value of the car that depends upon its age. And so there are a couple ways to do this, but again, I just try to write down a formula, and you can use the old standby if you just want to use the functional notation where the letters just don't represent the problem you're working with, but you can write down a formula with it. That's fine. I probably would say, okay, I'm looking for a formula for the value. So I'm going to write v of t, and all I need to know is the initial value, which is v naught, and then the growth or decay factor. In this case, it's a decay factor because it says it's decreasing by 12%. And so my initial value, of course, is $9,749. And my decay factor, so let's try to figure out my decay factor, there's something to the t here. Well, it's decaying by 12%. So remember, 12% is a decimal, it's just 0.12. And decay means you subtract. So basically the idea is you take 1 minus 0.12. Or you can think about it, you lost 12%, you have 88% left. So this should be 0.88, which it is. So I always like to think of it as percentages. I don't have to remember these sort of formula ideas. So it's 9,749 times 0.88 to the t. Now, what will it be worth in 2 years? So you got to figure out, what do you do with that number 2? Do you plug it in for v, or do you plug it in for t? And of course, t, it's time stuff, so you plug it in for t. So this is saying, what is v of 2, which would be equal to $9,749 times 0.88 to the 2. And you'll need a calculator for this, so take out your calculator. Let's turn mine on here. And let's get out of here so second quit. And we'll need to solve this problem. So it's just basically a plug and chug, right? So it's 9,749 times, and then it's 0.88 squared. So 0.88. And if you want, you can raise it to 2 or just square it. I'll raise it to the 2. And you hit enter, and we get out this number. So $7,549.63. So let's just round this to the nearest dollar. So let's say $7,550. So approximately $7,550. I think that's what I said, right? Let's check. So $7,550 if we round to the nearest dollar. All right, so that's my answer for this one. And then let's look below it, because below it, this was really an input question, meaning you plug in for the input and find the output. This one's going to be, of course, an output question. It's sort of the opposite of what we just did, or inverse of what we just did in a way. And what year will the car be worth $5,000? So on this one, instead of plugging in for t, you're going to plug in, so instead of plugging in for t, you're going to plug in for v. And when I say v, I mean this is all of v, right? So you're going to plug in right here. So v of t, the output, is 5,000. So 5,000 is going to be equal to, and on the right-hand side, you have the formula, 9,749 times 0.88 to the t. Now, this one's not so easy to solve. It's not a plug and chug. You have to solve the exponential equation, which we did last time. So let's solve this. So how do you solve this equation? You want to solve for t. So the first thing you have to do is you have to get rid of that 9,749 on the right. Because you know the idea, you want to bring that t down, and the only way to do that is to L on both sides, but you got to get rid of that number there first. So we move it over by dividing, so you have 9,749. Divide that on both sides, 9,749. And so on the left-hand side, you don't want to simplify this. You just want to leave it alone, because you don't want to approximate until the very end, otherwise we'll lose information in between. And so we have this on the left, and on the right we have just 0.88 to the t. And now to move down that exponent, remember, the idea is we can take out this tool, we call it ln. And for us right now, ln is just a tool that brings down exponents. So we'll ln this side, and we'll ln that side, which we don't change the equation. But what's nice about ln's is it'll bring that exponent down in front. And so what we'll get here is on the left we'll have ln of 5,000 divided by 9,749. And on the right-hand side, that t gets to come down in front, so we have t ln of 0.88. And so we're almost done. We're trying to solve for t here, so whenever you get stuck, you can always say, I'm trying to solve for t, so that's what you want to leave alone. So what we'll do is we need to move over this ln of 0.88. And remember, this is all one thing. So what we're going to do is, since you have t times ln of 0.88, we're just going to divide both sides by it. I'm going to divide both sides by ln of 0.88 on the right and on the left, so you don't change the equation at all. And that's going to give us our value for t. So t will be equal to exactly, we write it down exactly, so ln of 5,000 divided by ln, ln of 5,000 divided by 9,749, so it's all in parentheses, ln of all that, then divided by ln of 0.88. And now to figure out what that is, we can basically approximate it with our calculator. So on our calculator, I have it written down exactly here, I can approximate this. So I'm going to hit the ln button, so ln of 5,000 divided by $9,749 in parentheses, then divided by ln of 0.88. And it's going to spit out a number, and then I have to interpret how to use that number. And so I get about 5.22 years. So let's write that down. I get about 5.22 years. 5.22 years. And you could use this number, but it's not really the answer because it really says what? It says in what year. So you should do is you should go back and try to figure out, what year the car is the value. And so I'm going to guess it's this year because it doesn't tell us. So I'm guessing, it says 2018. And so right now, because it's currently worth, right? So it's telling us right here, it's currently worth that. So currently it's 2018. And so what I will do is I'll take 5.22 and add to 2018, and it'll tell me this is in the year. Well, if you add 2018 to it, it'll be 2023. So sometime in the year 2023, this car should be worth $5,000. Okay, so hopefully this helps to introduce you to what an exponential function is, this idea of constant percentage rate of change. You should be able to identify an exponential function from a table. You should be able to see that it, understand it has two graphs, one that grows and one that decays. From the formula, you can use this variable a, which is called the growth or decay factor, to determine whether it's growth or decay. You also have this variable c, which is the sort of initial value. And then we can do some modeling problems with this, so you can see how this can actually be used to model different situations.